Welcome to problem set 27. Our problems today are from the topic Metabolism, Krebs Cycle, and the Electron Transport Chain. Before we get started, just a quick reminder that the worksheet to accompany this problem set video is available online through my website. And with that said, let's go ahead and get started with number one. Number one, which of the following are exergonic processes overall? Circle all that apply. So in other words, which of these processes overall will release energy, are exergonic? So photosynthesis, that's the process in which plants convert carbon dioxide and water into glucose. And of course, the energy required for that process is absorbed from the sun. So this is a process that absorbs energy. That makes it an endergonic, not an exergonic process. So do not circle A. B, anabolism. Anabolism refers to the building up of larger biomolecules from smaller ones. And that process requires energy. So again, this is an endergonic process, not an exergonic one. So do not circle B. C, catabolism refers to the breakdown of foods that we eat to release the energy that is stored in their chemical bonds. So overall, catabolism is an exergonic process that releases the energy that is stored in the chemical bonds of the foods that we eat. So circle C. And D, combustion of a fuel. Combustion releases energy as well, primarily in the form of heat. So very similar overall reactions to what's happening in catabolism overall. If you look at the overall process of the breakdown of the foods, they're going to break down into carbon dioxide and water, just like a fuel, a hydrocarbon fuel would in a combustion reaction as well. But in the case of a combustion, it happens much more rapidly, and that energy is primarily released as heat. Okay, so circle combustion. That is also an exergonic process. All right, number two. What is the fate of acetyl coenzyme A in complete catabolism? Okay, so we already know that overall catabolism is taking the carbons, hydrogens, and oxygens from the foods that we eat and oxidizing them all the way to carbon dioxide and water. So the ultimate fate of acetyl coenzyme A is going to be complete conversion into carbon dioxide and water. Number three, how many carbons from the food source remain in one molecule of acetyl coenzyme A? So remember that it's the acetyl portion that comes from the food, and that's just the 2-carbon portion with a CH3 next to a carbonyl, and then that's connected through a thioester linkage to the thiol functional group that hangs off of the large organic molecule known as coenzyme A, which we just abbreviate as CoA. But notice this is not standing for carbon or anything directly, this is standing for coenzyme A. So the 2 carbons that came from the food are right here. So there are 2 carbons from the foods that we eat, and they are part of just that acetyl group. All right, number 4. How many ATP form, theoretical yield, when 1 mole of FADH2 is reoxidized during the electron transport chain and oxidative phosphorylation? So remember that we're using the theoretical yields. Some books might use the actual yields, and the theoretical yield for ATP synthesized when FADH2 is reoxidized later on in the electron transport chain and oxidative phosphorylation is 2. 2 ATP can form, theoretically, for every one, that's a 1, for every one FADH2 that's reoxidized. All right, getting a little bit busy on the board here, so let's erase before we go on to number 5. Okay, number 5. Is NAD plus the oxidized or the reduced form of the coenzyme nicotinamide adenine dinucleotide? Okay, so we're familiar with seeing this coenzyme in the form NAD plus and NADH, H plus. Okay. NAD plus is the oxidized form of the coenzyme. Once it picks up the hydrogen ions and the electrons, it becomes the reduced form, which is NADH, H plus. So this is the oxidized form of the coenzyme. Number 6. Refer to your answer from number 5. Is this form an oxidizing agent or a reducing agent? So in its oxidized form, it can be coupled to a reaction to oxidize a substrate by itself being reduced. So this is an oxidizing agent. That is, it will cause a substrate to be oxidized by then being reduced itself. So it's an oxidizing agent. All right, number 7. Refer to the Krebs cycle, slide number 5 of tutorial 27, to complete A through E below. So I'm going to grab my Krebs cycle here and hang it up on the board. And I'll refer to this as I go through A through E. Hopefully you have a copy in front of you, whether it's from my tutorial notes or one that you just pulled up on the internet with a quick Google search or your textbook or whatever the case may be, but you'll want a copy of the Krebs cycle to look at for these problems. So part A. Which step or which steps, plural, of the Krebs cycle involve an isomerase enzyme? Okay, so the isomerization is occurring on step 2 when citrate is isomerized into isocitrate. And all that's happening is that a tertiary alcohol is being rearranged into a secondary alcohol so that in the next step, the secondary alcohol can then be oxidized to a ketone. So it's step number 2 involves an isomerase enzyme. And we can look over here and see that the isomerase enzyme is a aconitase. So step number 2. Okay, part B. Which step or which steps, plural, of the Krebs cycle involve the oxidation of a substrate? Okay, so the oxidation of a substrate. The easiest way to look for the oxidation of a substrate is to look for the reduction of a coenzyme happening simultaneously. So let's go through all the steps. Step 1, I don't see any coenzymes. Okay, so let's go on to step 2. No coenzyme being reduced on step 2 either. But step 3, we can see that the coenzyme NAD plus is being reduced to NADH+. So step 3 must involve the oxidation of a substrate. So let's write step number 3. Are there more? Let's go on to step 4 and C. Step number 4 also involves the coenzyme NAD plus being reduced to NADH+. That means that a substrate is being oxidized. So let's write step number 4. Let's look at step number 5. No coenzymes being reduced there. Go on to step 6, and we have the coenzyme FAD being reduced to FADH2. So so a substrate must be oxidized. So let's write step number 6. Step number 7, we can just see that water is being added across a double bond. It's just a hydration, no coenzymes involved there. But step number 8, we see the coenzyme NAD+ being reduced to NADH+, so a substrate must be oxidized in step 8 as well. So I think that's the quickest, easiest way to look for those oxidation steps. Look for where the coenzyme is being reduced. And that is on step 3, 4, 6, and 8. Part C. In step 3 of the Krebs cycle, what is the substrate, the product, the enzyme, and the coenzyme? Whew, that's going to be a lot of work. Okay, so let me label those. We're going to say what the substrate is, what the product is. We're going to say what the enzyme is. And we're going to say what the coenzyme is. Okay, and this is all for step number 3. Okay. So you definitely want to have your Krebs cycle here unless you've memorized it. Some instructors might actually want you to memorize it. So we're on step 3. Isocitrate is being converted into alpha ketoglutarate. Okay, so on step 3, we're going to write for our substrate that we have isocitrate. Okay, that's our substrate. The product is the alpha ketoglutarate. And I'm going to go ahead and write carbon dioxide as well because we see that one of the carbons is lost from isocitrate as a CO2. So I'm going to write plus CO2. So that's where our first carbon dioxide is lost in the Krebs cycle. And the enzyme for step number 3, I wrote over here in this chart. Remember, it was a little too busy with all the enzyme names in it. So we just look it up over here for step 3. It's isocitrate dehydrogenase complex. That's quite a long one to write. Isocitrate dehydrogenase complex. Okay. Now we can kind of check here that makes sense because remember the enzyme names typically will tell you something about the substrate in which they act upon, and they'll tell you something about, typically, not always, but sometimes they'll tell you what kind of a reaction they're catalyzing. So dehydrogenase, so an oxidoreductase. That makes sense because we see an oxidation happening here. And then we have a coenzyme being reduced. The coenzyme is NAD+. And it's going to be reduced to NADH+ as the isocitrate gets oxidized to these products. All right, part D. We're running out of room here. Let's see if I can squeak it in. Part D. How many NADH+ and FADH2 result from one turn in the Krebs cycle? Okay, so this is something you might just want to memorize. But if you don't have it memorized, you can certainly look at the Krebs cycle and you can get the answer. I'm going to go ahead and write the answer and then I'll go to the Krebs cycle because I happen to have it memorized. Okay, so I happen to remember that 3 reduced coenzymes of NADH, H+, and 1 reduced coenzyme of FAD, H2, will be made per turn in the Krebs cycle. So let's go over here and see where I got that from. So if you don't have that memorized, you can still get that answer. Just look at the steps. Step 3, 4, and 8, kind of did this already up here, 3, 4, and 8, produce a reduced coenzyme of NADH+. So that's 3 steps making NADH+, so 3 NADH+. And then step 6 makes FADH2. So we have oxidation of substrate there, coenzyme being reduced to FADH2, so 1 FADH2. All right, and finally E. Let's see, do we have room? Yeah, we'll do E right over here, right under the Krebs cycle. Explain why the ATP yield from one turn in the Krebs cycle is 12 ATP theoretical yield. All right, so remember that all those reduced coenzymes that are formed in the Krebs cycle, they're going to be reoxidized in the electron transport chain, and the energy that is released from that process is going to be harnessed to power oxidative phosphorylation. That is the phosphorylation of ADP into ATP. So, writing my 3 NAD, H plus, and my 1 FAD, H2 up here, because they are intricately involved in the synthesis of the ATP. And then remember that on step 5, we actually get a high energy GTP. So I'm going to write here 1 GTP. And remember that GTP, guanosine triphosphate, is very similar to ATP, adenosine triphosphate. And so a lot of textbooks will just consider that to be 1 ATP yield right there. Okay, so that's what we're going to do. All right, so I like to do a little curly Q here to remind you that these 3 reduced coenzymes are going to be reoxidized later. This is going to happen later in the electron transport chain and oxidative phosphorylation. They are going to power the synthesis of ATP kind of indirectly in that way. And for every 1 NADH that gets reoxidized in the electron transport chain, enough energy is created to give you a theoretical yield of 3 ATP in oxidative phosphorylation. So we're going to do times 3 here. 3 times 3, that gives us 9 ATP later on in the electron transport chain and oxidative phosphorylation. Every FADH2 enters the electron transport chain at a later point, thus creating less energy and less ATP. So for the reoxidation of FADH2 in the electron transport chain, we're going to get enough energy to power the synthesis of 2, theoretical yield of 2 ATP. So times 2, and again, this is later on, so 2 ATP. When that FADH2 is reoxidized in the electron transport chain, it's going to release enough energy to be harnessed to power the synthesis of 2 ATP in oxidative phosphorylation. And then we're going to count our 1 GTP as an ATP. Again, most introductory textbooks will do that. So add it all together, we have 9, 10, 11, 12 ATP from 1 turn in Krebs cycle. Okay. So we've just shown how we get that theoretical yield of 12 ATP. Now real quick before we go, because this is our last problem, just a quick reminder, and I know I said this in the tutorial already, so hopefully it's not too annoying that I'm going to say it again, that these are the theoretical yields, times 3 and times 2, these are the theoretical yields, and some textbooks will use the actual yields of 2.5 and 1.5. And if your textbook or your instructor prefers to use the 2.5 and the 1.5, then the number you get here will be 3 times 2.5, so it's at 7.5, and then 1 times 1.5, so 1.5, and then 1. So you'll get 7.5 plus the 1.5, that'll give you 9, plus 1 will give you 10. So in that case, you'll get 10 ATP per turn in the Krebs cycle. And I'm starting to see those numbers used more and more in textbooks these days. So just be aware of that. The textbook I always taught from and the textbook I learned from used 3 and 2. But your textbook and your instructor may want you to use 2.5 and 1.5. And if that's the case, that's where the discrepancy comes from. Okay, so this will conclude our problem set 27, and I hope that you will consider tuning in to tutorial 28 as we continue to learn more about catabolism and talk about those specific pathways that the different food molecules take to become acetyl coenzyme A.